Whatever happened to modified Newtonian dynamics, that ambitious alternative to Einstein's gravity, which supposedly made dark matter superfluous? 2 years ago, some researchers claimed they'd all but killed it, but that proved to be rather controversial. Today I have 3 new papers, one with a new theory, and 2 much-needed updates about the data analysis. Let's have a look. Astrophysicists have many observations that they can't explain with normal gravity and normal matter combined, such as gravitational lenses that are too strong or galaxies that rotate too fast. They normally explain these observations with dark matter. That's some sort of matter that we've never seen in the laboratory, that makes up 80% of matter in the universe, and that makes itself noticeable only by its gravitational pull. The alternative explanation is to change something about the law of gravity. That is, one needs a modification of gravity. We can't just entirely kick out the law of gravity, of course, because we've measured it to high precision on Earth and in the solar system. So the idea of modified Newtonian dynamics, MOND for short, is that at some point the usual 1/r square law of Newtonian gravity must cross over into a 1/r law of modified gravity. This crossover should happen in the range of binary star systems. If they're close together, they should obey the laws of normal gravity, but if they're far apart, then they should feel the modified gravity. These far-apart binary systems are called wide binaries, and for a long time we had no good data for them. This, however, changed 2 years ago with the Gaia mission. The confusing thing is, though, that 2 camps did different analyses of the same data and arrived at different conclusions. One author said that MOND was confirmed, but another one said it was ruled out, and the first one made a mistake. But recently things have progressed. The first news is that the author who found support for MOND has addressed the criticism. He's now done a more sophisticated data analysis in which he reconstructed full 3D orbits for the binary systems. The result still prefers MOND at 4.2 sigma significance, so that moves my mondometer slightly to the MOND side. The second paper I have today comes from a third group, which said they did an independent test of the data, and they also think it supports Newtonian gravity and speaks against MOND. So that moves my mondometer back towards dark matter. Why can these people not agree? The issue is that some of the wide binaries in this data sample are actually triples. That's a close binary system with a third companion further off. These triples are hard to tell apart from wide binaries, but they would seemingly increase the acceleration exactly where MOND says it should increase. The discrepancy between the data analyses comes down to how the groups take care of the triple problem. The one method is to find a way to throw them all out. That's the case that supports Newtonian gravity. But the other camp says, no, you've thrown out the signal with it. You need to instead estimate the number of triples from short distances and then extrapolate. Honestly, I can see the rationale for both, so I think that debate isn't quite over. Meanwhile, we also have progress on the theory side. Pavel Krupa, one of the biggest and most outspoken supporters of MOND, has written a paper with several colleagues in which they present an improved version of MOND that they say can solve some problems. Ever since MOND was introduced in the 1980s by Mordechai Milgrom, it's had trouble explaining the motions observed in galaxy clusters. More recently, it also became apparent that it struggles with small galaxies, the so-called dwarf galaxies. In the new paper now, the authors introduce a generalized version of MOND that they say can explain the observations on galaxies and dwarf galaxies and galaxy clusters. Good thing, you might say. Yes, but it comes at the cost of introducing another parameter that basically interpolates between what is already an interpolation. I strongly doubt that this is going to convince critics. So after taking into account all 3 new papers, I've updated my priors and the mondometer still lingers on the dark side. MOND adds parameters, dark matter adds particles. I'm adding cheese, at least mine is edible. You've heard of zero-point energy, but have you heard of zero-point motion? Of the two, the zero-point motion is the harder to understand because it seems to create something out of nothing. That is motion from what actually? A new experiment has now shown that it's totally real. Let's have a look. Zero-point motion doesn't get remotely the attention that entanglement does, but I've always found it fascinating because it's such a direct manifestation of the randomness of quantum physics. And to me, it raises the question of whether that randomness is really fundamental or whether it comes from something else. But what is it? Let's start with zero-point energy. That's a purely quantum phenomenon that doesn't exist in the non-quantum world. It's a consequence of particles also being waves. Suppose you have a non-quantum particle and you catch it in some potential. That could be literally a dip on a surface, but it could also be a confinement with electromagnetic fields, which is how they do it in the laboratory. A particle without quantum properties will just sit there at the lowest energy point, and that's that. But if the particle has quantum properties, then it has a wavelength. And the wavelength needs to fit into the potential. This is the easiest to understand if the potential has hard walls, like it's a box. Then there are standing waves that fit in and the rest doesn't. This happens for any potential. And the important thing is that a quantum particle cannot not wave. It must wave. And if it waves, it has energy. This means that the state of lowest possible energy is above the classical no energy. And this is the so-called zero-point energy of a quantum system. It's energy that's always there, inevitably, because the particle has quantum properties. It's even still there at zero temperature. It's there in the vacuum. You cannot ever get rid of it. It's like emails from conferences you once attended. Okay, you might say, but who cares if it doesn't do anything? Well, this is where zero-point motion comes in, because the zero-point energy should be related to a zero-point motion. They're basically brothers. The zero-point energy should move stuff around randomly in some direction. I know this kind of sounds like magic, like you get motion from nothing, and that's totally correct. Physics is magic. This is what the math says anyway. It turned out to be very difficult to measure, though. There have been some previous attempts to look for zero-point motion in atom clouds, but that didn't properly work. This new approach works completely differently. They want to look at what the individual atoms do in a molecule. They have zero-point energy, but do they also have zero-point motion? Like, even if the molecule is not itself vibrating, it's the lowest possible energy state, can the atom still move because of this unavoidable energy? Common sense says no. Quantum math says yes. And the grant proposal says maybe if you give us $2 million. So what does the experiment say? They measure this with a method called Coulomb explosion imaging. They basically take a big molecule, then they blasted it with a huge X-ray laser. This rapidly strips off the electrons. Without the electrons, the atomic nuclei strongly repel each other because they're all positively charged. So the molecule explodes. They catch all the atoms and then they measure exactly what momentum each nucleus had. From this, they can infer how much zero-point motion the atoms had before the blast. It's a really clever method. And to make a long story short, they find that zero-point motion is totally real. I give this paper a 0 out of 10 on the bullshit meter. It's a neat experiment. I know that zero-point energy and zero-point motion attract a lot of attention as possible alternative energy sources, but I'm afraid I don't know any way to harness this energy for practical uses. unless your practical use is to confuse people on YouTube. However, I think that the theoretical implications are somewhat underrated, because think about it. The basic equation of quantum physics, the Schrödinger equation, has no random element. The only random element in quantum physics is the measurement process. So why does a molecule have zero-point motion before anyone's looking at it? Or does it not? Or is quantum physics wrong? I don't have an answer to this. I don't think anyone has. But for now, quantum mechanics has once again won a staring contest with common sense. Nuclear batteries are getting serious. Yes, I'm really talking about batteries that deliver energy from radioactivity. These used to be niche application things, but I've recently come across a few interesting patents that give me some idea of what's likely to come next. We've talked about nuclear batteries a few times before, but those were all small batteries with very low power output, like the Chinese company Betavolt, for example. They have this little battery that uses a radioactive isotope of nickel. It has a half-life of roughly 100 years and produces about 100 microwatt. There are also some companies in the United States which sell small nuclear batteries, like City Labs, that uses tritium, which has a half-life of about 12 years, and the British company Arkenlight that makes a battery from carbon-14, probably in the range of some microwatt at best, with a half-life of 5,000 years. Perfect if you want to leave something behind for your great-great-great-great-grandchildren that isn't an unpronounceable German family name. These nuclear batteries excel in their lifetime, and that has some uses like for sensors or some space missions. They are in the range of small button cell batteries, but because the power is so low, the range of applications is very limited. The interesting new development is now that the business is trending towards nuclear batteries with more power. One way this is happening is that the companies with small nuclear batteries want to stack them to reach higher voltage. For example, the company Infinite Power has put forward a patent with a battery that, going by this image, is about a cubic meter in size or so. They say that it can reach up to 3 watts. The Chinese company also says that one can combine their batteries from a few microwatts to several watts. Other than that statement, I haven't seen any details, but it's plausibly possible. So this still isn't huge, like you can't run a car with it, but at least it's enough to power a dim light. This sort of solution makes sense for applications where you need a long lifetime and aren't worried about space requirements. Ideal, for example, for some sort of beacons or measurement stations in remote locations. Maybe a webcam in Antarctica that sends penguin photos through the next millennium. But even more interesting is that some startups are moving on to a totally different type of nuclear battery called a radioisotope thermoelectric generator, RTG for short. You see, the previous batteries that I mentioned all use radioactive decay to create a flow of electricity. The reason they have fairly small power is the type of radioactive isotope that they use. But you can't use isotopes that radiate more power for these batteries, because then they'll just wreck the semiconductors you need to generate electricity. If you want higher power, you have to do something else, and that's to create power from the heat. And this is what these thermoelectric generators do. The idea isn't new. They've been around since the 1960s. NASA has used them to power some space missions. They typically ran on plutonium or polonium and reach up to some 100 watts. The Russians have also used strontium. The Russians actually deployed those things across the country for monitoring, for example, power lines. If you like true horror stories, in 2001, a group of Russians found such a nuclear battery that had been taken apart in the snowy wilderness and cuddled up to because it was nicely warm. It didn't end well. Very interesting video about this here. If you find an object that glows for unknown reasons in any part of the electromagnetic spectrum, please stay away from it. To come back to the topic, there are multiple companies that are advancing these thermoelectric generators at various sizes and watt levels, and rumors say that this might partly be used to power military drones, which sounds all too plausible. The American company Xenopower, for example, patented a new thermoelectric generator a few years back that reduces the size of these objects substantially, as you can see from this award-winning illustration. It could run, among other things, on strontium. Their website says they are developing nuclear thermoelectric generators in the range of 10 to 100 watts, and they do this for space, satellite, and seafloor missions, but I bet the military is very interested in this. The company NDB, which stands for Nano Diamond Batteries, has also extended its scope and now plans to build medium-sized nuclear thermoelectric generators in the range of a watt to kilowatts power as a heating solution for space and communities. Hauer Industries and NDB also work on nanoreactors. So these are actually nuclear reactors like the power plants that run on enriched uranium but produce energy in the range of some kilowatt to megawatt. I find this a very interesting development, though I can't help but think that the most plausible use case is post-apocalyptic bunkers. I just read this paper, and I think it makes a very strong point that gravity can't be a quantum theory. So Einstein was right after all. This is mind-bending stuff, but I'll give it a try. Physics can be abstract and unrelatable, but it's built on a key premise that we're all familiar with: causal order. You flip a switch, the light goes on. Cause, effect. One comes first, the other second. There's no ambiguity about this order. If you take into account quantum physics, the situation becomes more difficult. Imagine you have single quanta of light, photons, going through a beam splitter. The beam splitter converts each photon into a superposition of two directions. We often say that the photon is now both here and there. Now let's say on this photon's path we put two little gadgets that change the polarization. Let's also say that the photon started with a horizontal polarization. You can think of the polarization as an internal direction of the photon. The first gadget is one that'll rotate the polarization by 45 degrees right. The second one will flip it on the horizontal axis. What's the result? Well, it's now rotated by 45 degrees left. But the photon on the second path, we guide this, for example, with an optical fiber through these gadgets in the other order. It first gets flipped on the horizontal axis, but that doesn't do anything because it was horizontal. Then it gets rotated 45 degrees left. So you see, the order of these operations matters for the outcome. What one does then is set up an interferometer that recombines the paths and only gives a signal in output port 1 if the photon actually took both paths. So if that happens, then you know that the photon must in some sense have gone through these operations in both orders. So which one came first? You can't tell. That this indeed happens has been experimentally confirmed. It's called a quantum switch, and some have interpreted it as proof of an indefinite causal order. It's unclear what happened first to the photon. However, that claim doesn't hold up. You see, if the photons are actually in different polarization states, depending on which path they took, they can't interfere. To fix this, you need to effectively remove the operation you did on one path to get them to interfere. But once you've done that, there's no way to prove that the photon actually went both paths. Could just have gone either one path or the other and into the detector rather than both paths. Mystery solved, definite causal order restored. In quantum slang, they say that this indefinite causal order is not certifiable. The authors of the new paper have solved this problem by proving once and for all that causal order fundamentally deep down doesn't work. And the way they do this is to use general relativity. You see, Einstein taught us that mass and energy tell space-time how to curve, and that curvature tells light which paths to follow. In particular, if light goes into and out of a gravitational potential, that takes longer than as if the gravitational potential wasn't there. Now imagine you have a pair of particles in a superposition of two places, and you have two photons going by them. Now, depending on where the particles are, either the left photon arrives first or the right one. If those particles which bend the path of the light now are in both places, this is a true indefinite causal order. You can't tell which of the photons arrived first. The authors of the new paper now prove that if you could do this, there's some complicated arrangement of mirrors and switches and so on that no definite causal order can explain. I'll spare you the details because they aren't so relevant, and also just among you and I didn't understand them. But I read them twice, so I'm now confused at a much higher level. In any case, the bottom line is this. If there is a quantum theory of gravity, then causal order can't exist. I find this a remarkable result because you can turn it around and say, well, if we want a causal order, then gravity can't be quantum. Of course, if you actually put particles into the path of the photon, the gravitational effect is so tiny you can't measure it. You'd at the very least have to use mountains. Interesting, you might say, tell me more about moving mountains, but sorry, this is theoretical physics. We're not actually moving mountains, we're just thinking about what would happen if you did. In the unlikely event that this video caused you confusion, consider that maybe your confusion caused the video. Thanks for watching, see you tomorrow.